development stage. So the shaping, excuse me. So this is the most critical factor affecting the RCS of an object. Of an object is the geometry of the target, not necessarily in its size. And so engineers designed the B-2 aircraft in a way that the surface and the edges of the plane of the aircraft are structured in a way to reflect the radar energy and not return to it. So let's take into consideration the flat surfaces and the sharp angles of the B-2 aircraft. One can kind of conclude that it was designed to reflect the directions and not really back to the radar. Also, all sorts of bumps, curves, angular edges should be avoided, or rather was avoided for this purpose only. So so in that case, because of this reason in itself, any bomb, missile, large fuel tank set up externally would only increase the total RCS. So this is the reason why B-2 aircraft has a weapon set up internally, and also has to be carried internally too. The air intake design of the aircraft is also very critical when designing a low RCS aircraft, RCS. It is important to kind of note that the sharp corners and parallel surfaces also add to the total RCS. So the main goal in this case is always the same, which is reflect and the overall radar energy to irrelevant and random direction and keep the RCS low and making it stealth. So the radar absorbing materials. So this particular way of shaping design is an essential factor in achieving the RCS. So the other aspect, the shape is one aspect, and the other aspect is the use of radar absorbent materials, which absorb any specific portion of the radar energy and convert into heat energy. So kind of reducing the radar energy that needs to be reflected, which is the job of the first part. So kind of taking the load away from the first part, which is the shaping. It's also important to know that these materials don't absorb all the radar energy but rather is a supplementary approach to reducing the total RCS. It kind of works like a supplement. And the application of RAM, or radar absorbing materials, is also a trade-off, since they added, which is the trade-off part of the whole system engineering comes into play, because they added paint of coating, coating of the color and different kind of coating, which only adds to the overall cost and weight, and also limits performance. For example, the B-2 Spirit needs air-conditioned hangars and costly and limited maintenance to retain its low observable stealth capabilities. So it does come with a bit of trade-offs. So then I move on to the active cancellation. So it is based on the principle of creating an appropriate destructive echo, which would potentially potentially cancel the real limitation of the target from going back to the radar. As a result, the goal would be to emit electromagnetic energy properly in sync with radar energy and with current amplitude and phase to minimize the reflected signal and echo. So the technical difficulties are kind of out there apparent, such as converting the target into radar energy itself in case of wrong computation or implementation. That can cause could have caused further researches to be done, or adding more time to the overall preparation of the RCS. Excuse me. So the passive cancellation, it's also referred to as the impedance matching. It's based on the idea of creating an echo source whose amplitude and phase would be fine-tuned in a way to cancel another echo coming from the radar detection system. So this process tends to be easily achievable for simple objects. However, it gets increasingly complex for purposes like an aircraft, in case this B-2 Spirit. So that was the engineering developmental stage. And now I'm going to talk about the post-developmental stage. So the entire contract of the whole engineering responsibilities in mid developmental and post-developmental verification was developed in 6 different configuration. So they kind of looked at it at 5 different stages. So there's radar, avionics, low observable quality or stealth, software and embedded systems, and onboard flight control. So looking at those different criteria in the post stage, how they distributed all those jobs in different contractors. So it was distributed to many organizations in the execution of the systems engineering process in the post-development stage, and also checking, testing, and finalizing any kind of issues or errors that could have come. So the avionics rather. So avionics was it provided cooling, heating, and power, and a few other resources, and made sure the testings were done and it had proper results to what the researchers were getting. So it also defined requirements for the flying testbed, breadboard avionics system in the early and posted developmental stages. The flying testbed, it tested much of the equipment before it was flown on the B2 and after as well to confirm the functionality. The logistics systems engineering, its responsibilities related to supportability and interfaceability of a future weapon system, which was the B2. So this group established the criteria for supportability, requirements, and requirements for to each subsystem, system element, and structure assembly. So the bulk of the maintenance and in the post stages are performed on the surface treatment to maintain low observability, which is the main factor of B2 aircraft. The system engineering process mentioned in this part was a problem for the second and third generation stealth aircraft, and was included in the original risk mitigation plan. And also it's important that the logistics systems engineering group, this group established the criteria for supportability, requirements to each subsystem, system element, and structure assembly. They also published a design criterion based on lesson learned from similar equipment, and made sure the supportability was met for all the specifications, and established a detailed growth test for all the different system pieces of equipment. They also, I wanted to mention that they also very closely monitor the progress of the subcontractors within this contractor and the vendor design, and posted different kind of post developmental testing. It must also be noted that the logistics systems engineering team also developed the specification for all the automated test, training equipment, and directed the development of new processes so they came up with new processes to make sure the stealth quality is maintained on field. So a crucial role in achieving the RNM, which is the reliability and maintainability for the overall hardware and software, can be given to this group and this group only. So the weapon system. So it was founded mainly to focus on the evaluation of the weapon system's mission, effectiveness, survivability, and vulnerability of being attacked in the post-developmental phase in order to make sure it's minimized as much as possible. And also responsible for stealth technology evaluation. And also just wanted to briefly mention it's one of the group within this team was the vulnerability group, which had the responsibility of analyzing the aircraft's final design vulnerability that the model faced against conventional weapons, electromagnetic pulse, and different radar cross section, or RCS. So this group, the vulnerability group, also conducted further studies to make sure the plan provided the hardening of the aircraft against already at that time, the existing nuclear radiation. The later appointed specialists in nuclear hardening to help with the issue within the team. A test requirement was then established for the unique test facility in the USAF for the overall nuclear hardness. It's also given in detail in the report. So the VODs. So the VOD assigned their engineering work into an organization with the System Engineering Office and lead project WBS task team, leaders reporting answering director of the chief to the the chief engineer in charge of the B2. So they develop improved processes for fabrication and assembly of the inlet assembly. They built and tested and verified the post-developmental method for cooling the air deck assembly. So that brings me to the challenges and risks. So Northrop Grumman, who's the prime contractor for producing and assembling the aircraft, still faced difficulties in delivering the B2s that can meet Air Force operational guidelines and requirements, even after 9 years of work. For the most part, aircraft were delivered late. They're given late with significant deviation that happened the within different teams. The General Accounting Office, or the GAO, observed that the achieving the threshold radar level was still a difficult objective to achieve. So the GAO, or the General Accounting Office, also stated that certain radar signatures required for specified blocks do not really fully meet the contract specification. Excuse me. So the cost and developmental issues caused the overall price to rise significantly higher, which are also kept a secret, and not really much information or reports are found about that. So the investigative arm of Congress detailed this that week in 1991 in one of the report in New York Times that the world's most costly airplane breaks down in rain, warm temperature, and in humid environment. The report said that the skin of the plane can't handle the heat or the damp of the rain. So without this stealthiness, the plane is less than unique achievement the Air Force has claimed it to be. So as a consequence, the plane requires climate control shelters, which adds to the overall cost and the problems and more challenges. So the B2, excuse me. So the B2 engineers collectively came up with a risk closure plan as a tool to be used to process thoroughly and identify and mitigate all kind of problems and risks that may arise. And they're given in the bullet points where their avionics with definitions, subsystem approach and performance testing, reliability assessment and development growth testing, aeroelastic structural response, radar antenna design and construction of a working model, substantial scale, composite and radar absorbing structure development, which were mentioned in the engineering development phase in order to minimize the RCS, the aero propulsion integrating with the low observable requirements, the RCS testing and materials development, the inlet engine integration and the validation of aft deck airflow and temperature. So this previously mentioned segmented full-fledged dimension that I just mentioned, the risk closure plan was first proposed by Northrop, B2 program manager in the 1980s. It must be said, that it was a crucial program for almost 2.5 years of risk reduction and challenges that came with it, and precisely used to develop, the work plans on how to according act to different scenarios such as the weather, temperature, the climate control shelters, or any problem or any further researches that needed to be done about to maintain the stealth factor. So now the next part is a summary and lesson learned. Here I'm gonna draw some inspiration from the lecture slides and what I've taken up on different slides and different topics that I've learned in the course, and how I've applied that in order to kind of analyze and kind of take away from what good was done, or how certain thing could have been done differently in order to maybe improve the overall system designing phase from the B2 systems engineering. So one of the fundamental lessons that can be learned from the case study is the lack of focus put on the types of environmental interaction that the B2 was about to face. That's also been, we have learned that on one of the slides as a potential important thing that you want to consider on before you kind of come up with a certain system that's going to be out in the environment. So the secondary interaction, the secondary environmental interaction, it relates to the elements that interact with the system in an indirect manner, such as physical interacting with the weather and temperature. And examples for this case, how it lags. In this case, the examples can include support system, repair, in a highly temperature controlled maintenance center in which the B2 lacks significantly, in which they really don't put that much importance in secondary environmental interaction. So the B2 aircraft engineers did not give enough importance on how the maintenance will take place, where it will take place, what will be the cost, the trade-off, and the sheer human resources that will be required, given the complexity of the system. So the systems engineering process lacked the system engineering process lacked an advanced development phase process, in which the main objective is to kind of resolve the majority of uncertainty through analysis, researches, hours of work, and development, and to validate every single aspect of the overall system design as before going on to a full-scale engineering. So there are some unproven concepts used in the developmental phase of the B2 Spirit, in which the composite materials were required to be used for various parts of the B2 body. Composite materials mean that materials having two different kind of shapes of structure are combined in order to make a different kind of material, in this case, which is called composite material. Why I have an arrow saying lack of data? Because when they used that, they came up with an idea they need that composite material because the overall weight was getting much and much larger, and in order to have its ability to fly and still have all the functionality, they needed material that was going to be lighter and still have the same kind of quality. But there was a lack of data available in that materials when it was being built, so they didn't have significant data. They also didn't do significant researches before going on to the full-scale engineering and coming up with the composite material. This kind of came in the mid developmental phase. And but I want to end with the fact that in terms of pre-planning, the decision-making process, assessment of risk, that they mentioned the risk closure plan, and coming up with extensive plans to mitigate it, and dividing work, which is one of the fundamental things that I've taken from the overall case study, is dividing work from the government and the private contractor personnel, and give it to contractors, subcontractors, in a way that the whole system is not solely dependent on one team or one group or one company. As it's given to certain companies, and they all work together. They all report to the same department, and they all kind of come to a conclusion. If a trade-off has to be made, it's not just one company. It's if one company communicating with the other, one contractor communicating with the other contractor, and then coming up with a plan. So dividing the work among various contractors and still coming up with smooth transition across platforms. The B2 Spirit system engineering process, it does a tremendous job. So this is a very good case study that one can look at, and also look at my paper, and look at the presentation, and look at all the sources that I've cited, in case someone wants to learn a lot more on the system engineering process of how a very complex aircraft system is done. So that's my email, kaa532@nyu.edu. So in case you want to reach out to me with further any questions or something that I can hopefully answer, and I'll try to answer. So I'll be happy to. And so I just want to say this course has been a very eye-opening course for me, and because I'm interning at Leviton, where I work as an engineering intern, and there are multiple kind of not positions, but rather opportunity where I can work with product management team, the mechanical team. So I feel like the systems engineering course kind of gave me very extensive information in terms of different ways and how to look at things, and how to look at the product, the cost, the different teams such as mechanical, the thermal, electrical, and how they all kind of come together in order for one goal or objective to be met. So I just wanted to thank you for this course. This has been very helpful, and I hope I haven't bored you completely with a 30 minutes presentation, and it was somewhat enjoyable. And yes, and the paper, my paper does much more detailed explanation of each and every step, and also cites properly. So in case someone wants to take a broader look at different parts that were being worked on, they're happy to do so. So yes, so I've kind of looked at it in an overall perspective and not focus on just one part of the engineering phase and then look at how the system engineering is done. I looked at it in overall, and how the contractors kind of work together to achieve so and so task. And in the engineering developmental phase, I looked at the RCS, because I've kind of after doing extensive research, I kind of come to the conclusion that the B2 kind of stands on its own because of that RCS, which is the minimizing the RCS, or the low observable stealth, which is what's known for. So I've looked at that for the engineering developmental phase, and how they achieve it. What's the engineering or the computation method of the scientific method on how to do it, and then I moved on to the post and mid both, because they talk about working in between contractors and teams, and how, coming up with different tests in order to mitigate, analyze, and kind of, risk management issues, kind of risk management, and how also they, monitor even after the full scale engineering is done, in order, in any case certain things were to come up, certain problems that might come, certain challenges, they're met right away. So thank you for listening, and hope you have a good night. I'm going to upload this presentation right away. Thank you.